This video will cover the topic, using a graphing calculator to solve a system of linear and quadratic equations, basic. To find the solution to a system of equations using a graphing calculator, we graph each function and then use the graphing calculator tools to find the points of intersection. These points of intersection are the solutions to the system of equations. Let's take a look at an example. We're given the system of equations y equals negative 2x minus 7 and y equals negative 2x squared minus 12x minus 17. We can use a graphing calculator to solve the system of equations and round to the nearest hundredth. Let's begin by graphing the line y equals negative 2x minus 7. We can do this by clicking on the Alex Graphing Calculator button on the right side of our screen. From here, we can click the y equals button and enter the function y equals negative 2x minus 7 into the y1 equals spot. Next we click Graph to see a graph of our line. Every point on this line has coordinates that, when used in the equation, satisfy the equation. For example, let's look at the point negative 4, 1. We see from the graph that this point is on the line. We can also see that when we substitute x equals negative 4 and y equals 1 into the equation of the line, we will have 1 equals negative 2 times negative 4 minus 7. When simplified, the right side becomes 1, and we're left with 1 equals 1, which is true. This means that the point negative 4, 1 is on the line y equals negative 2x minus 7.
Will the coordinates of every point on the graph of a function satisfy the equation of the function?
They will. Just as in this case, the line contains all of the points that satisfy the equation y equals negative 2x minus 7. Now we'll graph the function y equals negative 2x squared minus 12x minus 17. Once again, we'll click on the y equals button, and this time we'll put our function in the y2 equals spot. And we click the graph button to see the graph of the function. When we do this, we see a curve. Similar to our previous example, this curve shows all points whose coordinates make this equation true.
What does it mean when we say find the solution or solutions to a system of equations? Is that the same as saying solve the system?
It is. If there's one point at which the line and the curve intersect, then that point contains coordinates that satisfy both equations, and we call that point a solution to the system of equations. If the line and the curve intersect at more than one point, then all points of intersection contain coordinates that satisfy both equations and are called solutions to the system of equations.
So can we solve the system of equations by finding those points?
We definitely can. In fact, the calculator has built-in tools to help us do this. If we go to the y equals button, we can make sure that both of our equations are checked. We can then select the intersect button, and we'll be given a few questions. For the first curve selected and second curve selected, we will want y1 and y2, assuming that we put our equations in the first two spots of the y equals page. For guess point, we'll want to enter an x value that looks close to the x value of the point of intersection we're trying to find. In this example, it looks like there's an intersection near x equals negative 1.5. So let's try that. Now we click Intersect, and the calculator tells us that there's an intersection at approximately negative 1.38, negative 4.24. If we click New, we can repeat these steps to find the x and y values at the second point of intersection.
Should we use a guess point of x equals negative 3.5?
That sounds good. When we do this and click Intersect, we find that the actual point of intersection is at approximately negative 3.62, 0.24.
So the solutions to the system of equation are negative 1.38, negative 4.24, and negative 3.62, 0.24?
Right. Let's see how that works. Let's take the first equation, y equals negative 2x minus 7, and substitute negative 1.38 in for x and negative 4.24 in for y. We see that this results in a true equation. Now we can substitute negative 1.38 in for x and negative 4.24 in for y into the second equation. When we do this, we get negative 4.24 equals negative 4.2488.
But negative 4.24 does not equal negative 4.2488. Does that mean we made a mistake?
Probably not. That discrepancy is most likely caused by the fact that we rounded our answers for x and y to the nearest second decimal place when we did the problem. To be sure that our answer is correct, we could go back and do the problem again to check our work.
Can we check the second point of intersection?
We can. We can check the second point of intersection just like we checked the first. We can plug the x-coordinate of the second point, negative 3.62, in for x, and the y-coordinate of the second point, 0.24, in for y, into the first equation. When we do this, we get 0.24 equals 0.24, so we know that we have a true equation. Next, we'll plug negative 3.62 in for x and 0.24 in for y into the second equation. After simplifying the right side, we get 0.24 equals 0.2312, which is fairly close, and since we've been approximating, this discrepancy is negligible. Now that we've checked our work, we know that the two solutions we found using our calculator earlier are the right answers.
So just to review, to find the solution to a system of equations using a graphing calculator, we graph both equations and then use the graphing calculator tools to find the points of intersection. These are the solutions to the system of equations.
That sounds perfect. Good work!